Alright, we are going to be solving problem 912 from the textbook. And this problem is about a tank which has continuous flow through it. Let's put some symbols on this drawing. We have a mass flow coming in. We have the same mass flow going out. We have a mass inside the tank, and we have a specific heat capacity of the contents of that tank. In this case, I believe it's water or something like water. The tank has an overall area, which we will call capital A, and it exchanges heat with the surroundings. And this heat exchange is characterized by an overall heat transfer coefficient. We'll call it capital U. Outside the tank, there's a temperature, an ambient temperature. I'll call it T air. There's a temperature inside the tank as well. And even though it's not part of the problem in the textbook, I would like to add some active heating of the tank by means of an electric heater. And I believe that's about it. So what we're going to do now, so the problem is to find out what's the temperature of the contents of this tank here. And to do that, we'll state an energy balance. So I'll start out by the general energy balance that we talked about earlier. So there might be work done to the system or by the system on its surroundings. There could be some exchange of heat. The flow in and out of the system supplies and takes away energy from the system. And if there's a reaction, that can also create energy or consume energy. And on the right hand side, we have the change in internal energy per time unit. So that's kind of the general energy balance. And well, it's a no-brainer to cross out this term here because there's no reaction going on in our tank here. And also we will neglect the work done on the system by the surroundings. We're talking about the agitator here. It does put some energy into the tank by this rotating movement, but it's minute compared to the energies involved with the heat, with the temperature changes and the heat supplied by the heater. So I think it's fair to neglect that work. Also, the volume work done by the system on the surroundings is neglectable because even though it might expand a little bit, that's just so little that it doesn't really matter. So we're left with this, and let's look at the different contributions here. The Q, the heat here, has a contribution from the active heating of the contents, so I'll call it Q dot. But there's also heat transfer going on with the surroundings, so that we can model by this overall heat transfer coefficient multiplied by the area times the temperature difference. I'll put the brackets here. So we have to figure out what temperature goes where. Well, let's look at the right hand side first then. This change in internal energy we can write as the specific heat capacity times the change of M times T, which is the temperature in the tank. I can't pull M outside yet because M could be changing since we have flow going in and out of the system. So that might be changing in time too. Is it a function of time? I don't know. But certainly temperature will be. So if the temperature goes up, so does the internal energy. So why would this contribute to the temperature going up? Well, that would be if the air temperature is higher than the temperature inside the tank. So if that's the case, this becomes a positive number. This term is positive, and it contributes to raising the temperature of the contents of the tank. So that's the right way here. T air minus T. Then we have the flow term here. So this term here. And we'll start out by just writing W in times the specific enthalpy, H in minus W out times the specific enthalpy of the outgoing components. Right. So let's see if we can simplify this equation. We'll do a quick mass balance. We don't really need to, but I'll just do it for completeness sake. So the mass going in per time unit, that's W in. And we have the accumulated mass, dm dt, and the mass going out is W out. So that means that dm dt equals W in minus W out. But since W in and W out are the same numbers, they're equal, this is 0. That means that dm dt is 0, which is to say that the mass inside the tank is constant. And W in equals W out equals W. There's no point in distinguishing between the two. So that simplifies our equation. So I'll just draw a line here. And we can write Q dot plus U A T air minus T plus W, the enthalpy of the incoming components, the enthalpy of the outgoing components, is equal to CV, and I can pull out the mass now because it's a constant, and I can write dt dt. So that simplifies it. Now the enthalpy of the incoming components we can write as the heat capacity at constant pressure times the temperature of the ingoing component minus some reference temperature. And the same thing goes for the outgoing components here. That's the difference in temperatures with respect to some reference temperature. Now that reference temperature is pretty much arbitrary in this case anyway, because it cancels out in the expression here. So what we get is Q dot plus UA T air minus T plus W CP times T in minus T out equals CV dot times M times dt dt. All right. Now, if we assume that the tank is well stirred, that means that the temperature of whatever goes out here is the same as the temperature of the contents of the tank. There's no temperature gradient inside the tank. So that means, basically, that means that T out is equal to T. And also, since we're dealing with a liquid, the two heat capacities are virtually equal to each other, so there's no point in distinguishing. So that further simplifies our equation here. Q dot plus U A T air minus T plus W C times T in minus T equals C times M times dt dt. That's as far as we can go. So now we have an energy balance, which is a first order. We can see here, first order differential equation. It's linear, and that means we can solve it manually, or we can do it in Python if we like.